Hello guys. So let's begin where we left off from last time, right? And before that, let's just recall some of the things that we have been talking about. So in general, we were interested in invertible linear maps, right? So we were interested in invertible linear maps, okay, and its implications, of course. So we recall some of the key facts, right? That a linear transformation has an inverse. If a linear transformation has an inverse, it's easy, right? So recall one, that if T inverse exists, right, where T is transformation from E to W and T inverse is a transformation from W to V, then T inverse is unique. Also recall that linear map is invertible. So T, I'm assuming T is linear, of course. So T is linear. So T is invertible if and only if T is 1-to-1 and onto. Okay, correct. And also, and this gives rise to an interesting idea about vector spaces, about two vector spaces V and W, and they are isomorphic. So V and W are isomorphic. Meaning identical structures. V and W are isomorphic if there is an invertible linear map from one vector space to another. So if T is invertible. Okay, all right. So in other words, I mean, we also proved a theorem which says that two finite dimensional vector spaces are isomorphic if and only if they have the same dimension. So there's a corollary of this. So this is the definition, right? This is just the definition. The corollary of it is that if V and W both are finite dimensional and T is linear, right? Then V and W have the same dimension. So V and W are isomorphic if and only if they have the same dimension. So V and W are isomorphic if and only if dimension of V is equal to dimension of W. And we are only talking about finite dimensional vector space. Okay, so these are some of the important results that we have seen. And as a consequence of this, I mean, what you can say is that what it implies is that every finite dimensional vector space is isomorphic to some array. Okay, all right. So this also implies every finite dimensional vector space is isomorphic to some Fn, which is, vector spaces of n dimension, can be real or complex, right? Fn or Rn, whichever way you want to look at it. Okay, all right. And uh, then what this also implies that if V is finite dimensional, if V is finite dimensional, then the dimension of V has to be equal to N. Okay. At this point of time, please understand that, I mean, a finite dimensional vector space, two finite dimensional vector spaces do not have to be necessarily the same, right? I mean, they could be very different in structure. Like, for example, if you recall the example that we discussed the other day, which is vector space of polynomials, right? I mean, in a vector space of polynomials, the basis vectors are polynomial functions, 1, x squared, x cubed, okay, all the way up to x to the power n minus 1. Okay, and then you could have a vector space of matrices, right? It just contains some set of matrices, like 2 by 2 matrices or whatever, right? Okay, so these both of the dimension of both of these vector spaces could be same, but the vector spaces themselves may not be the same, right? So that's the whole point. Okay, now I mean, so therefore there is a nice implication. You already know, also recall that you already know that a matrix induced by a linear transformation is nothing but a linear map, because it's easy to show, right? I mean, there are two properties of matrices that I have already shown, that the addition as well as the scalar multiplication both hold, right? Okay, so there is this in connotation that, if your transformation is an invertible linear transformation, which means if T is 1 to 1 and on 2, then the corresponding matrix is also invertible, right? Okay, so therefore what we do is, if we define a basis, in V, right? Basis in V, which is nothing but V1 through Vn, and we define a basis in W, which is nothing but W1 through Wm, right? Okay, then you have a mapping between n basis vectors in V and n basis vectors in W, and what it gives you is a matrix, right? What it gives you is an m by n matrix, right? M by n matrix defined over the set of real or complex numbers. Okay, as simple as that. Okay, so I mean, just to show the connection, I mean, so the matrix induced by the transformation is nothing but this, right? I mean, I can just write it out here: A11, A1n, makes sense, right? We have an m by n matrix, right? Okay, and that we know that T is a linear map from V to W. We know that you have defined the basis in V, defined the basis in W, right? And so therefore, this is very simple to see that T applied on any one of the basis vectors, right, will give us this. I can simply write this in the following manner, and we can verify this in a moment, right? And what would be the index of J? The index of J would be from 1 to n. So clearly this is A1 K. Index of K is from 1 to n, right? It's easy to see, right? So the first element is A11. The second element will be A21, because your index of J will change, right? And index of K will remain constant. Okay, and you will have W1, W2, Wn, and therefore if you do that, you typically what you are doing is that you are applying this transformation on the basis vector, and what you are getting is this. Okay, straightforward. All right. And obviously this matrix will be invertible if your transformation is 1 to 1 and on 2. Okay, all right. Okay, now typically what we do is, when we say mn of f, what we imply is that, it's a vector space which contains all m by n matrices. Okay, so it's a vector space, right, containing all m by n matrices. That is fine, right? And this is where we stopped. Okay, our stopping point was this. I asked you a question that what is the dimension of such vector? Okay, and I claimed that the dimension of this is just m times n. Okay, we stopped here, if you recall, right? Now, I mean, why is this? I mean, why is this true? I mean, this should directly follow from the way we have written our linear transformation, right? Okay, but to give you an example, just so that you can follow better, right? And then we'll come back to the intuitive explanation of this. So let's just take, you know, a vector space of, I'll just take it over the set of real numbers. Okay, so just all 2 by 2 matrices. Now, would you agree that a standard basis for this would be something like this? So you are just shifting the ones, right? And you can easily see, and each one of these is considered a basis element in your vector space of 2 by 2 matrices. And you can see that you cannot express any one of these as a combination of any of the other. And you can also see that this entire set, if you take a linear combination of this entire, all these elements, you actually recover the entire space of 2 by 2 matrices. So this is a basis, right? And so how many basis vectors do I have here? 4. So what is the dimension of? Right? So 4 can be written as 2 by 2. So similarly, the dimension of the vector space containing all m by n matrices will be m times n. Is there any other intuitive explanation for this? So when you have a vector space of m by n matrices, you actually have, you know, different m by n matrices which have 0 in all the entries except one, right? Except one entry, and let that one entry be a non-zero entry or a 1, right? How many such matrices you can cook up? M times n. And that is why the dimension or the length of the basis vectors in such a vector space is m times n. Okay, all right. Okay, now there is this, the next thing that I would like to talk here is that when we discussed about isomorphism, right, or when we discussed about invertibility of linear maps, because typically you can define a linear map from one vector space to another vector space, and these vector spaces are not necessarily the same, right? However, if the vector spaces are necessarily the same, which means you are defining a linear transformation from a vector space onto itself. Okay, so precisely now what I am looking at is the following. So precisely our attention is now focused on these very specific linear transformations which take elements of basis vectors from the vector space onto itself. Okay, so we call such linear transformations, C is linear, of course, as operators. Okay, all right. Now the question is, in order to if your T is defined from V to V, the question is, do I still need both invertibility, I mean both injectivity and surjectivity to show that T is invertible? Okay, so this is the question, right? Because I mean, there are plenty of examples where we can see that there is a linear transformation which is injective but not surjective, or there is a linear transformation which is surjective but not injective, right? Okay, I mean, assuming that you are able to define transformations between finite dimensional vector spaces, I mean, will those transformations which are injective, not subjective, subjective, not injective, will be invertible as well. Okay, invertible only for such cases, not for general cases. So that is our next question. Okay, so let's save this first. Okay, so we pose a question now, which is T linear and V is finite dimensional, and we define a transformation from V to V. The question is one-to-one and onto? I mean, or one-to and onto both required. Okay, what do you think? What do you think, guys? Hmm? Can we take a wild guess? Well, okay. My question was also there is one request, guys. When I am on the whiteboard, I mean, it sort of becomes difficult for me to go back and take a look at the chat box, right? So when I'm on the whiteboard, you can speak, and I'm asking a question, you can speak, right? So I understand somebody has written that one-to-one is required. Fine. I mean, is on-to required? Maybe. My question was, are both required? Because we have seen previously that in order to define an invertible linear map, right, we need both one-to-one and on-to if your vector spaces are different, like V and W. Okay. The question is slightly twisted now. It's slightly modified. So what do you think? In other words, I mean, can I say this? Okay, of course, I mean, this is just a claim, right? And we'll have to verify this, right? This is just a claim that suppose, and this is an equivalent statement of the question that I just posed. Suppose dimension of V is less than infinity, right? And T belongs to the set of linear operators, right? Which means T is from V to V, right? Then the following are this is a very, I mean, you know, common expression or an acronym in mathematics that these following are equivalent is written as TFA. Okay, all right. I mean, you are familiar with many of such acronyms in your SMS language. However, this was far before, you know, mobile phones came into picture. So this is very standard. Okay, the following are equivalent. And what are equivalent? There are three statements I'm writing. T is invertible. Okay. T is one-to-one. and T is on 2. So these are three different statements. So what I'm saying, what I'm claiming is that these three are equivalent, which means, I mean, if T is 1 to 1, that is sufficient. I mean, that is sufficient to show that T is invertible. If T is on 2, that is sufficient to show that T is invertible, right? And T 1 to 1 implies T is on 2 as well, okay? And so on and so forth. So there is like these three statements can go back and forth between them. That's what it means, right? Okay. Now, let's see, okay? Let's see if we can verify this, right? So let's verify this. Now, T is from V to V, and we start with the first statement. We say that T is invertible, right? So T is invertible. Now, if T is invertible, T will definitely be 1 to 1, right? I mean, irrespective of whether your transformation is from V to W or from V to V, right? So T is 1 to 1. There is no doubt in this. This is trivial, right? We already know this. So this means that statement A implies statement B. Okay, right? Now, let's suppose B holds. Now, suppose B holds. So we assume now that T is 1 to 1. Okay. All right. So if T is 1 to 1, what do we know about null of T? Guys?
It's 0.
0. Very good. Null of T is 0. And what does rank nullity theorem tells us? The dimension of range of T is nothing but dimension of V minus dimension of null of T, isn't it? Right? Well, since dimension of n of T, null of T is 0, right? Because null of T itself is 0, so this is 0. So this implies what? That dimension of range of T is nothing but dimension of T. Now, if we know that range of T is a subspace of V, right? Okay, and now we know that dimension of range of T is equal to dimension of V, which means what? Range of T is exactly V, right? So this means that range of T is exactly V, right? Which means what? T is onto. Okay, all right. So this implies that statement B gives us statement C. Okay, all right. Okay, now there is one other way to go, is that let's say statement C holds. Okay, so now let's say statement C holds. So T is on 2. Okay, all right. If since T is on 2, we know that range of T will be equal to the vector space itself, right? Which means that dimension of range of T will be equal to dimension of P, right? And from the rank nullity theorem, this implies that clearly, this implies that the dimension of null of T is equal to 0. Now, dimension of null of T equal to 0, we know that that implies that T is injective. Hold on, one second. Right? Okay. Right? So we know, what do we know? We know that we assume that T is on 2. We know that T is 1 to 1 now. So if T is 1 to and 1 to 1, then that means that T has to be invertible, right? So T has to be invertible, right? Okay. And this implies that statement C gives us statement C. Okay. Nice, right? It's a it's not an intimidating thing to show that, but what this tells us is that if I'm dealing with linear transformations that go from the vector space onto itself, either invertibility, I mean, or either one-to-oneness or onto-ness, that injectivity or subjectivity is enough to, show that C is an invertible linear map. Okay, so therefore, there is a statement that we need to summarize, and that is this, that for linear C going from V to V, V finite dimensional, right? Injectivity or subjectivity of C is sufficient for invertibility. Okay, all right, and this only applies to linear transformations between V to V. Okay, all right, great. This is a great result. Now we will have to, sort of do certain, examples. Okay, based on this. So let me get this first. All right, so let's just work out a few examples. So with this, we actually have covered everything between of chapters 1 to 3 from Sheldon-Exler's test. Okay, all right. Now I'm picking some examples, a few examples from Sheldon-Exler's book. Okay, that book you have seen do not have solved examples. Okay, so everything is an exercise. What I'm doing is I'm picking up some problems from the exercise and I'm trying to solve those for better understanding. Also, if you have noticed, I don't know how many of you noticed that I have posted the solution to the second homework. Okay, it's in the same thread where we posted the homework itself. Okay, all right. Okay, so this is the first example. Let's say I have a vector space V. Okay, vector space V, such that the dimension of the vector space is 1. Okay, all right, and therefore, and I define a linear transformation from the vector space onto itself. Okay, all right. So the claim is the following. The claim is the following, and it's really intuitive that there exists, and V is defined over the set of real or complex numbers. So there exists a scalar such that okay, all right. So what do you think? Could this be true? Just one-dimensional vector space, which means that the basis in such vector spaces is just one element, right? Your basis cannot contain more than one element. You can think of the set of real numbers or the set of complex numbers as examples. So what do you think? Can we express linear maps in this fashion? Please also note the precise representation of the vector v, right? The precise representation of the vector v is not known. The precise representation of v is unknown, which means that I really do not know. I cannot say that v is 1 or v is 3 or v is x. I don't know that, right? So therefore, what I should do is that I should have a a generic representation of an element, right? And you know that any element can be represented as, you take that element and you multiply it by its scalar, right? So that depending on the value of the scalar, you can, have the value of that element small or have the value of the element large. This is a very standard way of representing numbers, right? Okay. So since a precise representation of v is unknown, right? I can always, think of the mapping, right, as some scalar multiple of the basis element itself, right? Because the basis element contains, the basis contains just one element, right? You multiply it with a scalar, you get another basis, right? You multiply with a different scalar, you get another basis, right? Isn't it correct? And since you have the mapping T from V to V, right? So if I pick an element V in here, right? So when you are applying it, you are actually putting it back in V itself, right? So, and you can simply write it in the following manner, because it doesn't really matter, because you do not actually know the precise representation of the basis element, right? And by the virtue of the linear transformation, you have this, right? Okay, all right. And then you can come back, because your TV can also be, your TV can also be just V, right? Okay. Right. Okay. So it's just like this. It's like this. You have something like this, right? Okay. And your V could be anywhere along this line, okay, by virtue of this linear transformation T. Now, based on the transformation being a contraction or a dilation, right? You could have a larger value of V or a smaller value of V, right? You could have something like this in here. You could have something like this, right? A or whatever. Okay, all right. So it's just a choice of scalars. Okay, all right. So example 2. Slightly more trickier, okay? This is a more tricky example. Not tricky, this is, sort of, I think it's just you have to, think of or come up, quickly on your feet, right? So what I want from you is that, can you give me an example? Give an example of a function, because linear transformations are functions, right? They're a very special type of functions. Functions can be linear or non-linear, right? And a function which satisfies the two properties of additivity and scalar multiplication is called a linear transformation, that. But in this case, I'm just defining a function which is defined between r square and r, okay? Such that the scalar multiplication property is satisfied, okay, for all a in R, okay, right? And your vector V lies in R square, right? But F is not linear. Can you think of any example? Can you think of an example? Guys, any example, any function.
Sir, x square plus y square.
X square plus y square will satisfy this scalar multiplication property.
Oh, oh, sir, you wanted to. Okay, okay. I'm sorry.
Yeah, because the scalar, that's okay. The scalar multiplication property has to be satisfied, right? But f is not linear. I mean, which means it's a straightforward example. I mean, you have to think of a transformation which does not satisfy the additivity property. You know, transformations have two properties, right? Additivity and scalar multiplication.
Maybe root xy. I mean, okay, but then like. Sir,
Yeah,
let me think a bit more. Let me think.
Yeah, sure. I mean, all of you are at liberty to think. Okay. So I will just give you 2 minutes to think, and I'll move on to another example. Okay. All right. I'm just not giving the solution right away. So let me think of another. Let me talk about this example. Okay. Let's say I have a bunch of injective linear maps. Okay. So these are all injective linear maps. Okay. All of these are individually injective linear maps. Okay, such that when you take a composition of these linear maps, like S1, S2, S3, S all the way Sn together, right? The composition makes sense, right? So my question is the following: is when you take the composition, of all of these injective linear maps, is that composition injective as well? I mean, one-to-one. Okay, a simple way to show that is to just assume, let's say, that S1, S2, S10 of V equal to 0. Okay, in order to prove or disprove this, I mean, if you think this is true, all you have to show that this implies V is equal to 0, isn't it? Right? That's the definition of one-to-oneness, right? I mean, f of u equal to f of v implies u is equal to v. That's what one-to-one is, right? Now, I mean, I just start from here. Now, since it's a composition of linear maps, I can always write it as correct. Would you agree? Now, let's look at this carefully. What we know that individually each one of these maps are injective. So S1 is injective. So if S1 is injective and S1, S2, blah, blah, blah is equal to 0, then this guy must be 0 by the property of injectivity, right? Okay. Now, what does this mean? This means that you have S2, Sn, V equal to 0. Now, you can rewrite this in the following manner. And apply the same argument, right? This time the argument is that we know that S2 is also injective, right? So since S2 is injective, then this guy has to be 0, right? And so I can continue this argument in a chain, right? And if I come to the end of the chain, I will have this Sn of V equal to 0, right? Now, what we know is that Sn is 0. I mean, sorry, Sn is also injective, right? And Sn of V equal to 0. That means V must be 0. Okay. So, which means the composition of injective linear map is also injective. Okay. The same cannot be true. The same is not true about the division of injective linear maps. We don't know anything about that. Okay. But let's come back to example 2 now. Let's come back to, yeah.
X plus y squared by x.
Oh, okay. All right.
Is that would be
Let's see, right? Let's see. I don't know. So you are saying that your fxy is, what did you say? X plus
y
y
square
square.
by x.
The by x is the whole denominator or just the denominator of y square?
Sir, just the denominator of y square.
Okay. All
Sir,
right.
are you writing somewhere? I can't see it. Or is it?
Yeah, I mean, I'm on writing on the whiteboard, right? You can't see?
Sir, actually, it's lagging. I mean, you're writing something and it's being like we're able to see it like after 1 or 2 minutes.
Yeah, guys, there is no power here. So I'm connected to my 4G.
Okay.
There is no power on campus. I'm sorry. This is like, beyond my control. I'm really sorry. I'll try to, okay, I'll just, what to do, because I'm connected to the internet, but okay, okay, can you see the whiteboard now?
Sir, it's the Google Drive page that we're seeing.
Strange, because okay, 1 minute. See, I'm presenting full strength, okay, I'll just stop presenting and start presenting again, okay? So this maybe, I'm really sorry about this. Let me do this. Let me disconnect the whiteboard and connect it again. Before that, let me just save this, okay? Hold on, I'll just disconnect them. Okay, now let's go to okay. Guys, can you see the whiteboard now?
Yes, sir. The whiteboard is visible. Yeah.
Okay, all right. Sorry about that. Okay. So yeah, so this is the function that you have asked me to write, right? If you said that this is x plus y square over x, and you think that this will satisfy the scalar multiplicability condition. So how do we check this? How do we check this?
Sir, like write x as ax and y as ay, and then
Right, correct. So we have to see f of av, right? So f of av is that I can just take this as v1 and v2. So this is a v plus a square u square by a v, right? According to you. So this is a v plus a u square by v, right? Which is a v plus u square by v. And this is nothing but a of v. Excellent. Yes, right? So this satisfies the scalar multiplicability property, but does it satisfy the additive property, which is f of, what is an additive property? Okay, so let me erase this, right? I have already saved this whiteboard, and I'm sorry for the fiasco earlier. You should have told me much earlier that you were not able to see anything on the screen.
Sir, no, sir. I think only at that moment it stopped like
Oh, okay.
updating.
Okay. Let me. Okay. So can I? Okay. Now the injectivity property is this. Okay. So the injectivity property is this, that I will write, I need to show that f of x1 plus x2 is not equal to f of x1 plus f of x2. This is what I need to verify, right? Now, what is f of x1? F of x1 is nothing but x1 plus y1 square by x1, right? And what is f of x2? F of x2 is x2 plus y2 square by x2. Okay? And what is f of x1 plus x2? F of x1 plus x2 is x1 plus x2 plus y1 plus y2 squared by x1 plus. Now clearly these will not be equal, right? Because the moment you open up the y1 plus y2 square, you have an extra term, which is 2y1 by 2, which is not accounted for when you take the sum of f of x1 plus f of x2. So clearly this is not equal. All right, good, very good example. Okay, I mean, I had another example in mind, but I mean, I should settle with this one. That is good enough, right? And there are plenty of such examples. Okay, so never mind. Okay, good. So I have to save this as well, right? All right. Now let's take another slightly bigger. I mean, even though these are nice examples, there is one slightly trickier problem, right? Okay. And the problem is this. Okay. Let me know if it stopped or if there is any lag or you are not able to see what I'm writing on the whiteboard. Okay, I'll immediately stop. So suppose that P is a linear map from V to F. Okay, all right. Now prove that if U is a vector in V, okay, and U is not in null of T, okay, then V can be written as a direct sum of null of T and a vector representation like so this is the second component, is just a set of all vectors of the form a scalar times that vector, right? Okay. All right. Now, if you recall, do you recall the definition of direct sum? It means, I mean, a vector space, if you recall, we have talked about this in the context of support vector machines, right? In the context of orthogonal subspaces, in the context of orthogonal complements, right? That if a vector space can be decomposed into two subspaces, such that when you add those two subspaces, you actually recover the entire vector space in such a way that the intersection of those two subspaces is null. Okay, all right. So in other words, in order to show that the statement is true, what we really need to show is that we need to show two things. One is that the intersection of null of T, right? The intersection of null of T and AU has to be 0. Okay, that's one thing that we have to show. We have to show that since we have to actually show that V is equal to null of T plus AU, which means, I mean, the one way of showing this is that you pick for all vectors in V, all vectors in null of T, and all vectors in this guy, such that, okay, need to show that. Because if you are able to show this, that implicitly tells us that the vector space V itself is a sum of, an algebraic sum of null of T and the set containing A. Okay, all right. So we just proceed with the first one. Okay, all right. And these two directly follow from the definition of direct sum. Okay, so you have to first show. So in this one standard trick is just take some elements. So for all x which is in null of T intersection AU, right? Okay. We take
Sir,
yes.
what is AU?
Oh, AU is a set of vectors. Okay. I mean, and that set of vectors is that it's another vector space, but it contains vectors in a very specific form, right? It only contains vectors which are scalar multiples of another vector U. That's what it is. It is also another vector space. Okay. Please recall. Please
So
recall
F here,
that, right? F is the set of real or complex numbers because your
so
vector
the field.
space, right? It's a field, right? So it's your linear transformation takes you from a vector space V to a field. Okay. All right. Okay. So you can think of an inner product that way. I mean, inner product, that's exactly that, right? Okay. So we take X, right? So let's say X is some A star U, right? And so A star U belongs to null of T. Because since if X belongs to null of T intersection AU, X will belong to null of T as well. We know that. And we just consider such an X as some scalar multiple of U. Okay? All right. So this implies that by definition, T of A star U, this is certainly not what I tend to write. T of A star U, right? So T of A star U, because A star U belongs to null of T, T of A star U has to be 0, right? which means that A star TU is 0 by the property of linear transformation because T is linear, right? But what you also know is that U is not in null of T. This is given to us, right? U is not in null of T, correct? Okay, that means T of U cannot be equal to 0. So if T of U cannot be equal to 0, what it implies is that A hash has to be equal to 0, right? Okay. Now, if A hash equal to 0, you have constructed all elements in the intersection as A hash U. So this has to be 0. Okay, and therefore null of E intersection AU. Okay, all right. This is only the first part. Okay. The second part I have about 3 minutes, so I'll finish quickly. Okay. But I need to do some trick because I'm running out of space. Okay. So I'll start here for 2. Okay. Now I just write alpha in the following manner. I can do that, right? I can do that in such a way that, see, I have to show that this is what I have to show, right? That alpha equal to beta plus gamma. Now I construct beta in the following manner. I say that beta is alpha minus A star U, okay, and gamma is A double star. Okay, is my construction okay? I think, and as far as gamma is concerned, my construction is fine, right? Because gamma belongs to that vector space which contains all vectors which are a scalar combination of scalar multiple of the vector U, right? Okay, so the construction of gamma is fine. The construction of beta is just from intuition, because if I have to split alpha into beta and gamma, and I wrote it in this following manner, I have to write the beta in this. Okay, now whether this makes sense or not is something that we need to specify. Okay, I make another assumption. I also say that this scalar multiple A double hash is nothing but, it's a constant, right? So P of, so annoying. I will just say that okay, just some construction. Okay, just some construction of the scalar. It will be clear to you in a moment why I did such a construction. Okay, all right. So by virtue of this, my beta is now by virtue of this, my beta is now alpha minus T alpha by TU of U. Okay, now what I need to show is that, I have written it in the following manner. What I did was I have written alpha as a sum of beta plus gamma. But what I need to show is that such a decomposition makes sense in the following manner, that this beta has to belong to null of T, right? Now, does this beta belong to null of T, right? So, does this beta, does beta belong to null of T? The easiest way to see that is to quickly check what is T of beta, right? Because if you are able to show that T of beta equal to 0, that will be it. Now, what is T of beta? T of beta is nothing but right? But by virtue of linear transformation, by the properties of linear transformation, this could be split up, right? Decomposed. So T of alpha minus T of alpha by T of u. Guys, does this make sense? It's a simple algebraic operation. I just followed the property that T is a linear transformation. I applied it on a scalar on a combination of vectors, right? And by virtue of the property of linear transformation, I can decompose this. But now, look at the beauty of this. This TU and TU cancel out, right? Now, when TU and TU cancel out, you are left with T alpha minus T alpha. What is that? What is that? Isn't that 0? Isn't that what we are supposed to show? We are supposed to show that beta is in the null space of T. In other words, T of beta equal to 0, right? This is the reason I constructed beta in the following manner, and I assume that A double hash is like this. Okay. Now the second part, there is no problem, right? The gamma part is no problem, because gamma, by such construction, gamma, it belongs to the set of, or the vector space containing these sort of vectors, right? So what did we just show? We show that if you pick any vector from the vector space V, right? So we just show that. What we just show is that if you pick a vector alpha in V, you can write alpha as an algebraic sum of beta and gamma, where beta belongs to null of T and gamma belongs to AU, where A is. Okay, all right. So the two properties of direct sum are satisfied, and you can write, therefore, that the such a vector space can be written as a direct sum of null of T. Okay, all right, great. All right, that's it for today.
Sir?
Yep.
I just I saw the solution you've put for homework 2.
Yeah.
Yeah, sir, like the question was to prove that the eigenvectors of distinct eigenvalues were orthogonal, right?
Oh, okay. I mean, I show that they are linearly independent. That's okay. I mean, I'll look at your solution. Don't worry. Okay. All right. And I will put up a modified, revised solution. Okay. But were you guys able to figure out the problem? Did you guys prove by using the principle of mathematical induction?
Yeah.
Okay, fine. So that's it. Don't worry about it. I will. Don't just ignore it. I mean, I'll update. I'll post a new solution.
Okay. And sir, marks for homework 1.
Yeah, I'll update, because see, what happened was, yeah, I am updating it offline. Okay, so don't worry.
Okay.
Don't worry about your marks.
Yes, sir.
Now, just learn the stuff. Okay. All right.
Yeah. Okay.
Okay.
Thank you, sir.
Yeah.